Thermodynamic systems. There are different types of thermodynamic systems I will be talking about. First, the definition. What is a system? A system in thermodynamics refers to that part of universe in which observations are made and remaining universe constitutes the surrounding. Now when we say surroundings, it's just nearby region. So if this is the system, suppose this is a container where reaction is taking place or any phase conversion taking place, for example ice to water, water to ice, etc., then this is system. Nearby region is surrounding, and obviously this whole is in the universe. Next, which type of systems we will be talking about? The first one is open system. In open system, matter, work and heat, all three can be transferred. So matter can go out, get into, for example steam can go out of the system. Work can be done on the system or by the system. Heat can get transferred into the system or from the system, depending on whether it is endothermic reaction or exothermic reaction. Then closed system. In closed system, these two will be there, but matter cannot get transferred. It is closed, so that's why matter cannot get transferred. Other two will be there. So work can be done on the system, can be done by the system. Heat can get transferred into system or can go out of the system. Then we have isolated system. As the name suggests, it is completely isolated. So nothing can be done. So if any reaction is taking place here, if the temperature rises, it will rise because heat cannot get transferred. Okay. If any work is done on the system within the reaction, for example here, then it will remain inside the system. It cannot go out. We cannot work onto the system. The system cannot work on the surroundings. Nothing can be done. It is isolated. So that's why sometimes it is also said that it does not have any surroundings. The reason is because it doesn't experience any surrounding. It can't interact with the surroundings. Next one, adiabatic system. This is typical one. In this case, only work can be done. No matter can get transferred and no heat can get transferred. So that's why we say only work can be done on the system or by the system. Also, we can write Q is 0. Why? Because heat transferred will be 0. Heat cannot be transferred into system or out of system. Similarly, matter cannot get transferred. So also matter, no. Only work. And because only work can be done, we represent this work as WAD. AD indicates it is under adiabatic conditions. In this case, the walls are known as adiabatic walls. Adiabatic walls are those walls which do not allow transfer of heat. Adiabatic walls. And the process is known as adiabatic process. An adiabatic system, as I said, there is no transfer of heat between the system and surroundings. Only work can be done. So if any matter is there, it will remain inside the system. If any energy is produced, it will remain inside the system. Only work can be done. The manner in which the state of such a system may be changed is called adiabatic process. So whatever is happening inside, that is called adiabatic process. Then sign conventions. These are very important because sometimes this will make your answer wrong if you don't consider the sign correctly. The value is taken positive. Value of what? Value of work or heat. Means value of energy I am talking about. So sign convention for energies, work and heat, both are energies. It is taken positive if work is done on the system and energy is given to the system. So understand it diagrammatically. If we do any work on the system, if we transfer heat to the system, it will be positive. Positive work, positive heat. And obviously it will be negative if the work is done by the system or heat is transferred from the system. In that case, it will be negative. Now, state variables. What are state variables? I will be referring to these quite frequently in this chapter. The variables which describe the state of a gas. These are called state variables or also state functions. Same thing, whether you call them state variables or state functions, same thing. What is the definition? Those variables which describe the state of a gas. Okay, so for example, pressure, volume, temperature, and amount. So suppose, how to understand it? Suppose I have carbon dioxide gas. Okay, carbon dioxide gas, and I have pressure 1 atm. Okay, volume say it is 1 liter, temperature say it is 50 degrees Celsius. Okay, amount say it is 1 mole. Obviously it will be in gaseous phase here, so the state is gaseous here. Now if I apply pressure onto it, I continue increasing the pressure, and also I decrease the temperature below 31 degrees Celsius. There is something I will be talking about later on, critical temperature. Okay, but I am specifically mentioning the temperature here as say 30 degrees Celsius. It has to be less than 30.98. That is the critical temperature. Then it can be liquefied. So if we have very high pressure now, okay, instead of 1 atm, it is still 1 liter, it is still CO2, but if we now apply very high pressure, it can be liquefied. So state changes. So pressure, volume, temperature, amount, all these decide the state of a gas. So these variables are known as state variable. Another important point, state variables do not depend how the change is brought about. So if I change the pressure from 1 atm to 20 atm, say, it will not depend on how I did that. If I apply very high pressure here, the state will change. Whether it changes in 1 minute, whether it changes in 1 hour, that does not matter. That will not decide the state. The state will be exactly same whether you brought about this change of 20 atm in 1 minute or 1 hour. So because it does not depend on the path, it does not depend on the time, that's why this is a state function. It only depends on initial and final state. Whatever is the change, that will depend on only initial and final state, not on how you changed it. The functions which depend on the path, means how you brought about the change, those are known as path variables or path functions. So that's why you should remember state functions which do not depend on path, they depend only on initial and final states, versus path functions. Path functions are those ones which depend on how you bring about the change. So for example, heat. So if you provide heat for 1 minute or if you provide heat for 1 hour, the final result will be different. So heat will be path function. Values of state functions depend only on state, that is initial and final, and not on how it is reached. Volume of water, as I said earlier also, volume of water in a pond, for example, is a state function because it will depend on how much difference in the volume took place. But whether it was through rainwater, whether it was from tube well water, it will not bother about it. It will not depend on that. Now the concept of internal energy as a state function. First, we need to understand what is internal energy. There are various energies in a system, and there are few energies even we are not aware of. Okay, so that's why we say that internal energy is a combination of chemical energy, electrical energy, mechanical energy, and any other type of energy which we are not aware of. The sum will be internal energy. Now, because we cannot calculate these energies which we are not aware of, we cannot calculate the absolute value of internal energy. So if you are asked what is the internal energy of a system, we will not be able to say unless it is stationary, not doing anything in its standard state. Okay, we will not be able to do anything about absolute value of internal energy. So the sum of all these is the energy of the system, which is known as internal energy of the system. But still we can calculate the difference in internal energy. How? Because suppose internal energy is X, we don't know, but it is X. U1, internal energy, is represented by U. It is X. And suppose we provided Q amount of heat to it. So if we provided Q amount of heat, now its energy will be X plus energy provided to it, that is Q. It means we can calculate the difference U2 minus U1. Delta U will be U2 minus U1, that is X plus Q, minus X, that is Q. So we can certainly say that whatever work we done, whatever energy we provided, whatever heat we provided, or whatever change in work, change in heat, change in energy taking place, that is the change in internal energy. Thus, thermodynamics is, in thermodynamics we call it internal energy, that is U of the system. The internal energy changes when, okay, whether matter is changed. So suppose you have 100 gram of matter and you have 200 grams of matter, the internal energy obviously will be double, okay. Whether you do work on the system or work done by system, whether you provide heat to the system or heat released from the system, in all cases the internal energy of the system will change. So here I have taken example of open system. Whether it is closed system, then also work and heat can change. If it is adiabatic system, then also work can be done there. So in that case the internal energy can be changed. So when heat passes into or out of the system, when work is done on or by the system, or mass enters or leaves the system, in all cases the internal energy will change. We will consider in this chapter mostly that matter is same. We are not changing the matter. It is conservation of mass also. So during the reaction, matter is not changed. So largely our discussions will be heat and work related. Now the question, choose the correct answer. A thermodynamic state function is a quantity used to determine the heat changes? No, I said that heat is actually path function, if you remember. Whose value is independent of path? Yes, it does not depend on path. It only depends, state function only depends on states, that is initial state and final state. But let's consider third and fourth option also. Used to determine pressure, volume, work? No. This is just depending on initial and final state. Whose value depends on temperature only? No, we did not talk anything about temperature here. Only this depends only on initial and final state. It means the second option is correct. The value does not depend on the path. It depends only on initial and final states, state function or state variables. Then first law of thermodynamics. For that we will consider two parameters, work and heat, because the energy of the system can be changed by these two. Remember, we are not changing the matter, we are not changing the mass here. So that's why, as I said, only work and energy can change the internal energy. So if it is work, we will consider the adiabatic system, okay, means we are not considering any heat change here. No change done by heat, the change is done by work only. So in that case, internal energy of a system can be changed by doing work system on the system or work done by the system. Let the work done on the adiabatic system is WAD. Why I am saying here adiabatic system? Because here we are not considering any concept of heat change. We are not changing heat, only work is being done. Then change in internal energy obviously will be whatever energy is changed due to the work done by the system or on the system. So internal energy U of the system is a state function. It depends only on initial and final values. The positive sign here expresses that WAD is positive, that is work is done on the system. If the work is done by the system, in that case we will consider WAD as negative. Second one, internal energy can be changed by heat only. So in this case, we are not doing any work, only heat we are considering. So in that case, what can happen? Delta U, that is the change in internal energy, will be whatever energy is changed due to that heat. This V just indicates that here it is at constant volume. Why we are saying constant volume? Because work is not being done. If you know, the work is represented by, in chemistry, the pressure multiplied by change in volume, delta V. Okay, so here if I keep the constant volume, then I can ensure that work done will be 0. In this case I am considering change due to heat only, so I have to keep the work 0. I can keep the work 0 if volume is constant, delta V is 0, and in that case the work done will be 0. So in this case the walls of the system are thermally conducting walls. In general case, what we do, that we consider both. We are doing work and we are providing heat also, okay, or vice versa. The work is done by the system or the heat is evolved from the system. In that case, the change in the internal energy obviously will be due to both. So we can write Q plus W. This is very important equation we will be using very frequently. Change in internal energy is equal to Q plus W, that is heat change plus work done on the system or by the system. Remember, Q and W will be positive if it is on the system, to the system. Heat is provided to the system, work is done on the system. If heat is released from the system, it will be negative. If work is done by the system, it will be negative in that case. This is also known as first law of thermodynamics. Okay. Another point which is important and question appears from here. If you remember, I said that delta U is a state function because it depends only on the state, that is initial state and final state. You get the difference, you get the value of delta U. But Q and W both are work functions, path functions. So how could it be possible that path functions are equal to state function? The answer is, although individually they are path functions, but Q plus W as a whole is a state function. So if you are asked this question, this is the answer. Q plus W is equal to delta U, which is a state function. So this whole sum is actually state function. Individually, yes, Q and W are path functions. So first law of thermodynamics, as I said, this is actually the first law of thermodynamics, the mathematical form. If I write it in words, I will say the energy of an isolated system is constant. How? Because if it is isolated system, as I said, nothing is done. If you remember, in isolated system, nothing, no work can be done, no heat can be transferred. Matter obviously not getting transferred. So if W is 0, Q is 0, obviously delta U will be 0. If delta U is 0, delta U will be W plus Q, that is 0 here. If delta U is 0, it means change is 0, change in internal energy is 0. If change is 0, it means the internal energy is constant. So the energy of an isolated system is constant. That is actually proved by this mathematical equation. So in words, first law of thermodynamics, the energy of an isolated system is constant. Mathematically, delta U equals to Q plus W. So this is actually the law of conservation of energy. The energy is conserved. If it is not going out, if it is not getting in, then it will be constant. It cannot be created, it cannot be destroyed. So law of conservation of energy. Now the question. Express the change in internal energy of a system when no heat is absorbed by the system from the surroundings, but work is done on the system. So we need to find delta U, and we know that delta U is equal to Q plus W. Change in internal energy we need to find, and it is written no heat is absorbed. So if no heat is absorbed, Q is 0. Work is done on the system. If it is done on the system, it will be positive. So it means delta U will be plus W. What type of wall does the system have? So if you remember, I said that if no heat is transferred, work is done, it is adiabatic system. So it means you will write delta U is actually plus WAD, and no heat is getting transferred. That's why it is adiabatic system. So what type of wall will it have? It will have adiabatic wall. So delta U is equal to WAD and wall is adiabatic. Next part of this one, again you have to find change in internal energy. No work is done. So delta U equals to Q plus W, first law of thermodynamics, mathematical form of first law of thermodynamics. No work is done, it means W is 0. But Q amount of heat is taken out of the system. If it is going out of the system, it is negative. It means it will be minus Q. So delta U will be in this case minus Q. Now the question is, what type of wall does the system have? Work is not being done, but heat is getting transferred. So it means the walls have to be thermally conducting walls. So delta U will be minus Q and walls thermally conducting walls. Next part of the same question. Again, find the change in internal energy, which is given by Q plus W. W amount of work is done by the system. If it is by the system, it is plus W. Sorry, if it is done by the system, it is minus W. If it is done on the system, it is positive. Okay. And Q amount of heat is supplied to the system. So heat is supplied to the system and work is done by the system. So this one positive, this one negative. So delta U will be equal to Q minus W. What type of system it is? Now it is not wall, system has been asked. Okay, so work is being done and heat is getting transferred, but no matter is getting transferred. It is not written, so you should not assume anything. Okay, so you will not say open system, you will say closed system, because no information about matter transfer is given there. So delta U will be Q minus W and it is closed system. Now work done in irreversible process. Irreversible process, what is irreversible process? The process which continues in one direction and it is fast. Fast and in one direction only, means reverse direction is not possible. So that's why written irreversible. It will be fast. So suppose you have a piston. You have a piston and there is gas inside and you compress it. When you compress it, the piston will come here. It will move here. Okay. So you are pressing it in one direction. You are not moving in the opposite direction and you are doing it very fast. So at any point of time, you certainly know in which direction it is moving. It is so fast that you know the direction. So this type of system will be known as irreversible system and the process is termed as irreversible process. So as I gave you the example, if I apply external pressure Px, okay, and it moves towards left and it is very fast, then obviously I will say it is irreversible process, because at any point of time I know in which direction it is moving. The work done in this case, okay, in case of irreversible process, the work done is given by minus P external delta V. This minus sign is just taken to comply with the sign convention. Okay, if we don't have this minus sign, then our sign convention that the work done on the system is positive and work done by the system will be negative will fail. So that's why this negative sign is there. So if the question is why this negative sign is there, your answer will be simple: to comply with the sign convention that work done on the system is positive, work done by the system is negative. Then work done in reversible process. Reversible process are slow processes. So if a process is happening very slowly, very slow, okay, so much slow that at any point of time you can't say whether it is moving in right direction or in left direction. So suppose you are applying pressure. I consider the same example, okay. You are applying the pressure on the piston, but you are applying pressure so slowly that at any point of time the piston looks it is stable or stationary. Okay. At that point of time, P external will be actually equal to P internal, approximately P internal. I am writing just approximately, but if it is ideal reversible process, we will say these are actually equal at any point of time. The reaction or the process is very, very slow. So when the direction of the process can be changed by slight change in pressure in this case. So suppose you apply delta P pressure in this direction, which is infinitesimally small. Okay, so because it is infinitesimally small, instead of writing delta P, usually we write it like delta P, lowercase delta P, okay, to show that it is actually continuous process. If you have done integration and differentiation, you should know this, okay, or if not done, you will do it in math. So in this case, at any point of time, you don't know in which direction the reaction is moving, and the direction can be changed by slight change in the conditions. In this case, slight change in pressure, then it is known as reversible process. So a reversible process proceeds infinitely slowly by a series of equilibrium states. Equilibrium states means stationary states. P external is equal to P internal, equilibrium, such that system and surroundings are always in near equilibrium with each other. In a reversible system, at any point of time, the internal pressure is almost equal to the external pressure. This is, we have talked about. The formula which you need to remember, and you will be using it in numericals, W reversible is given by minus integration over Vi to V final, V initial to V final, P external dV. Now you don't need to use this formula like this, okay? We will simplify this formula so that the usable form you remember. But you should remember this one also, because the questions are asked directly based on this form of formula also. Although not calculations, but this form of formula. So here, because P external is equal to P internal, we can write it as P internal also. So both formulas are correct because it is reversible process. P external and P internal will be equal. Now, for a pressure P, volume V, for n moles at temperature T, this is the ideal gas equation. For an ideal gas, this is the equation. If you multiply its pressure and volume, it will be equal to its number of moles, gas constant, and temperature. Gas constant R is 8.314 joule per Kelvin per mole, or if you represent it into ATM liter, then it will be 0.0821 ATM liter per Kelvin per mole. If you represent it in bar liter, then it will be 0.0831 bar liter per Kelvin per mole. So therefore, we can get from here, we can get the value of pressure, because if you remember in previous question, we have pressure, but dV. So obviously we can't do calculations if one is pressure, the other one is volume. So we have to convert this pressure in terms of volume, and we can convert this pressure in terms of volume by this equation. Okay, so pressure from here can be equal to nRT by V. So if we write this is pressure equals to nRT by V, and we substitute it into this equation, we will get this value. So if you have not done integration, you will not be able to understand how we have done it, but you have to remember this formula, that W reversible will be equal to minus 2.303 nRT log V final divided by V initial. This is ln, log base E. Log base E we have converted into log base 10, and when we convert log base E, that is ln is also written as log base E, it will be 2.303 times log at base 10. So that's why this 2.303 is there. You have to remember this formula, important one. Then free expansion and isothermal process I will consider in next class.